Hello friends, welcome back. We were discussing about the basic concepts related to bipolar junction transistors in our previous video. In this video, we will be seeing more about the terminal currents. Terminal currents means the emitter current, the base current, the collector current. And we will be deriving mathematical expressions for these terminal currents in this video. In this session, we will be deriving an expression for the terminal currents of a BJT. And as you all know, there are two types of BJTs, NPN and PNP. As it was our convention, we will select one type of transistor and do the derivation for that particular type, which can be like related or adjusted for the expression for the other type. So in this video we will be making use of the PNP type of transistor. Before doing that, we shall see few assumptions that we take during the derivation. First one is the hole diffuse from emitter to collector and the drift is negligible in the base region. The second assumption is the emitter current is made up of entirely of holes. As you all know, the PNP, emitter is P-type, base is N-type and collector is P-type. So the emitter current is made up of the holes, which is the majority carriers in the P-type semiconductor. And because of that, the emitter injection efficiency gamma is equal to 1. The third assumption is that the collector saturation current is negligible. The next assumption is that the active part of the base, which is the center position of the base, and the two junctions, emitter base junction and collector base junction, are of uniform cross-sectional area A, and the current flow in the base is essentially one-dimensional from emitter to collector, and above all these assumptions, we assume that the currents and voltages are steady state. As I had mentioned, in today's derivation we will be considering a PNP transistor, and the figure shows the connections that we are making so that an emitter current flows from the emitter to the collector through base. And also there is a base current which compensates the recombination in the base. And also you have to give concentration onto the distance. The 0th position is at the edge of emitter base junction, and the holes from the emitter moves from emitter to the collector, and the distance traveled is xn, where xn is at the edge of the collector base junction. If you remember that I had mentioned in the previous video regarding the base width. Base width is normally the available area, the active area in base between the depletion region, this area. So this connection will be the basis of all the equations that we will be writing regarding the terminal currents of the PNP transistor. So since the injected holes are assumed to flow from emitter to collector by diffusion, we are just revisiting the assumption. Diffusion. Drift is considered as negligible. Please do keep in mind the current inside the PN junction is due to diffusion and drift, if you remember. So here we are just considering the diffusion. We can evaluate the currents crossing the two junctions. The two junctions are the emitter base junction and the collector base junction by the techniques that we have already used for PN junction. Here we are neglecting recombination in the depletion region. Here we are having two depletion regions, which means that the whole current entering the base at emitter junction will be IE, and the whole current leaving the base will be IC, the collector current. And if we can solve the distribution of excess holes in the base region, it will be just a gradient of distribution. That is what we do in the derivation of finding terminal currents. So keep the figure that I had shown earlier in mind, where the base width is WB between two depletion region, and the area of cross section is A throughout. Certain notations that we use in our derivation is to be also understood. Ne0 will be the equilibrium electron concentration in emitter, which is mathematically put as Ni square, which is the equilibrium electron concentration, intrinsic electron concentration that we had seen, Ni, divided by NAE. NAE is the number of acceptor impurities in emitter. Why we are putting, normally earlier in PN junction we were just using Na. Here we are using NAE as notation because there is a difference in doping for emitter and collector. Though both are p-type, the doping concentration will be more, or the emitter will be heavily doped when compared to collector, which is moderately doped. That's why we are using NAE for emitter and NAC for collector. Similarly, PB0 will be the equilibrium hole concentration in base region. Equilibrium hole concentration in base region. And NC0 is the equilibrium electron concentration in collector region. We are considering PNP transistor, so we know that electrons will be minority in the emitter. Same is the case with collector, where electrons are minority. In base, holes will be minority. Why we are bothered of the minority carriers? Because that is the cos for excess carriers. Another notations that you have to keep in mind is delta PE, concentration of holes injected from emitter to base at emitter end of the base, where in the diagram, if you remember, x equal to 0 or the starting point, and delta NE is concentration of electrons injected from base to emitter at the edge of the depletion layer. Similarly, delta PC, concentration of holes injected from collector to base. And delta NC is the concentration of electrons injected from base to collector. So keep these notations in mind as we proceed in our derivation. The excess hole concentration at the edge of the emitter depletion region and the corresponding concentration of collector side of the base, delta PC, can be found using the equations. Delta PE will be equal to Pn e raised to QVEB by KT minus 1. Similarly, delta PC, if you remember, is the concentration of hole injected from collector to base, will be equal to Pn e raised to QVCB by KT minus 1, where VEB is the voltage applied at the junction, emitter and base junction. That is why VEB. And VCB is the voltage applied between collector base junction. And this can be simplified if emitter base junction is strongly forward biased, then this can be written as approximately equal to, since emitter base junction is strongly forward bias, we can write Pn e raised to QVEB by KT, neglecting that one. Similarly, delta PC can be approximately equated to, if the collector junction is strongly reverse biased, this will be equal to minus Pn, neglecting this term. Now, from the continuity equation for holes, from the diffusion equation of holes, if we are in the continuity equation, since we are considering only the diffusion equation, we will have d square by dx square of delta P of x is equal to delta P of x by LP square, where LP is the diffusion length. As we have done solution for the second order differential equation, here also we are making use of that. Delta, the solution will be delta Px will be equal to C1, a constant, e raised to minus x by LP, plus C2 e raised to minus x by plus x by LP. X by LP. Now applying the boundary conditions at x is equal to 0. Remember the diagram. Then delta Px will be equal to delta Pe. Why? Because it is the edge of the emitter base junction, and at x is equal to WB, delta Px will be equal to delta Pc at the edge of the other edge of the base, which is nearer to the collector. Now applying these boundary conditions, we will get two equations. Applying x is equal to 0 in the equation, the solution equation 1, we will get delta Pe is equal to C1 plus C2, because in place of x we are putting 0. X you are putting 0. So e raised to 0 is 1. So we will have C1 plus C2. Similarly, by applying the second boundary condition, x is equal to WB, we get delta Pc is equal to C1 e raised to minus WB by LP plus C2 e raised to WB by LP. Substituting in place of x, we are substituting WB. Now in order to solve, we are having two equations now. If we are having two equations and we need to find two variables, we can solve for it. What we can do is that multiply equation 1, if we are using the same equation number, that will be a problem. Here we can put as 2 and 3. In equation 2, if we multiply equation 2 by e raised to minus WB by LP and then subtracting, C1 terms will get cancelled and we'll get delta Pe into e raised to minus WB by LP minus delta Pc is equal to C2 e raised to minus WB by LP minus e raised to WB by LP. or C2, by rearranging we can write C2 is equal to delta P E raised to minus WB by LP minus delta PC all divided by E raised to minus WB by LP minus E raised to WB by LP. This is C2. We can call it as equation number 4. Similarly, by adjusting we will get C1 as delta P E minus C2 from the equation number 2, where we know delta PE is equal to C1 plus C2. From that we can find C1. So which will be equal to delta PE minus this equation, delta PE E raised to minus WB by LP minus delta PC by E raised to minus WB by LP minus E raised to WB by LP. This is in bracket. This is in bracket, which can be simplified and written as delta PE E raised to WB by LP minus delta PC by E raised to WB by LP minus E raised to minus WB by LP. This is C1 and this is our equation number 5. Sorry. So the two equations or the solutions for the constant C1 and C2 is obtained, and now you can substitute these values in the solution equation. Solution equation, as you remember, is delta P of X, which is the excess all concentration at the point X, is C1 E raised to minus X by LP plus C2 E raised to X by LP, which I had seen earlier. And substituting the values of C1 and C2 here, we will get a bigger equation. C1 is delta P E raised to WB, maybe a small b, WB by LP minus delta PC divided by E raised to WB by LP minus E raised to minus WB by LP into E raised to minus X by LP plus delta PC minus delta PE E raised to minus WB by LP all divided by E raised to minus WB by LP sorry, e raised to WB by LP. This minus is being adjusted by WB by LP minus e raised to minus WB by LP. Into, this term is remaining, into e raised to x by LP. As you see, the denominators are the same. We can group delta PE terms and delta PC terms in the numerator and simplify the above equation and write as the denominator we have e raised to WB by LP minus e raised to minus WB by LP, and in the numerator we will have delta PE terms together, which is e raised to WB minus x by LP, because e raised to minus x by LP is multiplied inside. So e raised to a into e raised to b is e raised to a plus b. And in this term we will have e raised to minus of WB minus x by LP, and plus delta PC. By grouping terms of delta PC, we will have e raised to x by LP minus e raised to minus x by LP. So this is the simplified version of the above equation. And by the mathematical knowledge that we have, we can write e raised to x minus e raised to minus x, this term as sin h of x. So this can be simplified and written as delta PE sin h, hyperbolic sin h of WB minus x by LP, and delta PC, again using the mathematical knowledge, we are rewriting it as sin h x by LP, and in denominator we can split and write again sin h WB by LP. Here also we have sin h WB by LP. So that is the delta P of x, and the current due to this excess carrier can be written as, from the diffusion equation, making use of the diffusion equation, IP of x is equal to minus QA, area of cross section, dP, diffusion coefficient, d by dx of delta P of x. Remember the diffusion equation, and in place of this delta P of x we can substitute the obtained value. So that QA dP by LP, C1 e raised to minus x by LP minus C2 e raised to x by LP. And we know at x equal to 0, IP of E is equal to IP of x. This is at x equal to 0. So we can write it as IP of E is equal to QA A should be in the top. I'll just rub it off. QA dP by LP C1 minus C2. We already know C1 and C2. Substituting those two terms here, we'll get QA dP by LP C1 is, as you know, delta PE e raised to WB by LP minus delta PC, and C2 is delta PC plus delta PE e raised to minus WB by LP. Sorry, this is the substitution from the previous equation that we had found for C1 and C2, and the denominator is e raised to WB by LP minus e raised to minus WB by LP. This is pure substitution. There is no big deal in that. Now group delta PE terms and delta PC terms so that we get, and also applying the mathematical knowledge that we have, e raised to WB by LP plus e raised to minus WB by LP can be written as cos h. So now we have 2 delta PE cos h of WB by LP. I'm just skipping one step so that you can fill it up. 2 delta PC. We are having 2 delta PC, all divided by 2 sin h WB by LP. This can be further substituted or simplified by taking the cos h divided by sin h is cot h. That knowledge we are making use of, so that this can be written as QA dP by LP delta PE cot h WB by LP. minus 1 by sin h is cosec h. That can be written as delta Pc cosec h Wb by Lp. Similarly, we know at x is equal to Wb, the other end of the base, it is IPC, the collector current, or IPC will be equal to IPX at x equal to Wb. Remember the diagram. At x is equal to 0, IPE is equal to IPX. That is what we used in the previous equation. So that this can be written as QA dP by Lp C1 e raised to minus Wb by Lp minus C2 e raised to minus illa, there is no minus, Wb by Lp, which can be further simplified by substituting values of C1, so that we get QA dP by Lp into delta PE cosec h Wb by Lp minus delta Pc cot h Wb by Lp. Cosec h Wb by Lp and cot h Wb by Lp. The derivation is similar to the previous segment. That's why I have written just substituting C1 and C2, you will end up at this point. Similarly, INE, which is the current due to electron injection from base to emitter, can be evaluated and found as equal to QA dN by Ln at the emitter side, delta Ne cot H hyperbolic cot W E by Lne. And the current due to electron injection from base to collector, INC, will be equal to minus QA dN ln dNc ln C delta NC cot H WC by ln C. Now we will make use of these terms. These terms means the IPE equation, this equation, and INE equation to find IE, the total emitter current IE will be equal to IPE plus INE. By substituting the derived equations, we will get Q A dP by LP. Just what we do is just substitution. Delta PE cot H WB by LP minus delta PC cosec H WB by LP. This is IP of IPE. This is IPE plus INE, which is QA DNE by LNE. We are using extra E's to show that it is in the emitter side. Delta NE cot H WE by LNE. This is the emitter current IE. Similarly, IC, which is equal to minus IPC plus INC. We can write it as this minus sign is there, minus QA. Minus sign shows the direction of the current. So it is an opposite direction we are taking. Minus QA dP by LP, just substituting. Delta PE cosec H WB by LP minus delta PC cot H WB by LP. This is small b, since we are using that, which shows its base. If you are using capital B, you can use it throughout the derivation. Since we were using small b, that's why I have changed to small b. Plus INC, which is QA DNC by LNC. Here the C denotes the collector side. Delta NC cot H WC by LNC. This is the collector current. Now the remaining terminal current is IB, which is equal to minus of IC plus IE. We already know IE and IC. Why the minus is being put in case of collector current and base current? Remember the diagram where the emitter current is entering the transistor and the base current and collector current is leaving the transistor. That direction is being shown by this negative sign. So we have seen equations for IE, IC and IB. That completes our derivation of terminal current of the transistor. Here we have made use of PNP transistor. Similar equations can be written for NPN transistors also by making the necessary comparative changes.